took the test before the class.
The second time I feel pretty well, right? Just the good option on the way out, I don't go. Kyle finished the 8 and everybody finished. What good
Okay guys, let's start. So today, for the second half of the tutorial, it'll be a first tutorial, but basically TAs will just flash questions on the screen and then you just drop it here, we'll be around, ask questions, get to know our transfer and so on and so forth. So it's more of a hands-on activity than it is sit down and just listen to what I say. Okay, so before I continue where I left off, any questions from last week or any comments on last lesson? Anything? Suggestions, comments, feedback, or questions? Okay, so just remind you, we are plowing on in some math background. We will get to the physics, but I really want to ensure everyone's on the same footing before we get to the physics. Okay, so since all of us know what vectors are, and we have begun our preliminary foray into linear maps or linear operators, let's just have a quick fire question. Make sure that everyone's on the same page, right? Okay, so simple question. Let's start like this. Suppose that we have a two-dimensional vector space, well, with an inner product. Okay. So let's have a basis on it. Standard one, I'm going to call it 0 and 1. And I give it to you that this is orthonormal basis. So what it means is that if I take the overlap I and j, that is delta by j. Okay, everyone knows that. Great. So it's a basis because the two vectors are orthogonal. So one can be represented by the other one. The space is two-dimensional, so there are two of them. They can span everything. Now my question is, suppose I define these states. Suppose let me define y plus, okay, and there's a reason why I call it y. Y is a physics notation eventually, but for now let's just treat it as a math question. Let's suppose I define it as 1 over the square root of 0 plus I 1, and y minus is equals to 1 over the square root of 0 minus I 1. So my question is, given these states, does y plus, y minus form an orthonormal basis? All right. First thoughts, someone? Quickly, so that I can move on to linear operators, but I want everyone to be on the same page. So, who says yes? Okay, some. Who says no? No? No one? So by democracy, answer is yes. Right? Right. What's democracy? Just okay, so we do some calculations, right? So what do we have to show? We have to show two things, right? We have to show that it's orthogonal, like the two states are orthogonal, they are normalized, and they form a basis. Okay? So very good. Let's check orthogonal first. So we need to do something like this: y plus and y minus. The overlap of y plus and y minus. And by the way, let me just remind you that once I find the overlap of y plus and y minus, I know automatically the overlap of y minus and y plus, right? Because they're just related by a complex conjugate. So once I've done the calculation, then I know what the overlap is with the other one, the opposite. Right? Everyone following me? Okay, so let's do it. How do we do this? How do we find the overlap? Everyone? Anyone?
You change the track to a bra for the white
Yeah,
line.
exactly. Very good, very good. Okay, so as the notation suggests, we have to calculate the bra and the cat to form the bracket. We are given the two cats. So the y minus, you know what it is. Now we need to know what the y plus is. Okay, good. So that's equals to something times something. And let's do the y minus first. Y minus is just exactly what I'm looking down here. Okay. And the y plus, I have to form the graph, which is take the adjoint of it. So what do? Apply the adjoint operation on this side. What does the adjoint do? The adjoint is a map that maps you from cat to graph and flips all the coefficients. So don't forget, the coefficient here in front of the 0 state is 1 over square root 2. The coefficient in front of the 1 state is I over square root 2. So I need to apply the complex conjugation of both of them. But that's real. So the first guy is 1 over square root 2, 0. Right? That's after applying the adjoint in the first term. Now apply the adjoint in the second term. The complex conjugate of I is
Negative.
I, very good. Okay, so then what we can do, okay, we can do a bit of simplification first. Let's just pull out all the factors of square root 2 because they're common, right? So I can write this as 1/2 times 0 minus I 1 times 0 minus I. Okay, everyone following? All I've done is just pull out the common factors of 1 and square root 2, which are just numbers, so I can just do that, right? Okay, then next I have to evaluate these peanut products. But because I've given this to you that the basis, the 0, 1 states are orthonormal, then you notice that you completed, okay, so in principle you would have to do overlap of 0, 0, 0, 1, 1, 0, 1, 1. But in this special case, when it's given to you that the 0 and 1 states are orthogonal and orthonormal, then it suffices to look at the diagonal terms, the 0, 0, and the 1, 1 term only. So we get 1/2 times 0, 0 plus minus I times minus I of 1, 1. And that's equals to 1/2 times 1 plus, so what's minus I squared? Minus 1, good. Times 1, that's equals to 0. Good, so they're orthogonal. And that also means that this is 0, that's 0, but automatically, as I told you, this is also 0 then. Because that's the complex conjugate of the right hand side. But the complex conjugate of 0 is 0, so that's it. Okay, so good. The ortho part is found. Now let's do the normalized part. Okay? So I know the lecture is very bad to write over whatever I've written, but to save space, let me do that. Let me adopt this best practice. So we can repeat the calculation for overlap of y plus and y plus, right? We want to understand this normalized. So what do? All we do is just change the notation. So we want to calculate something like this, y plus y plus. Okay, all right. So the first object was whatever we had done before, but this one is a plus, right? So if you carry through everything, you get a plus. What changes here is a plus, and then minus I times plus I is a 1, and that's equals to 2 over 2 is 1. Fine. Okay, so this is 1. Hopefully that was not too quick. Alright, let's track the minus signs. Next one, let's check if the y minus is also normalized. So let's put the minus here. And we have to form the graph of the minus state. We take the adjoint here. This minus I becomes a plus I, so we get this minus plus minus plus minus. And at the end of the day, that's still plus 1. Okay, good. So it's normalized also. And last step, is it a basis? Well, because the two states are linearly independent and the vector space is two-dimensional, so then, they'll definitely span everything. Good. Next question. Yes, any questions here so far? Okay, so what's the point of this exercise? Okay, I'm getting to a point. So because these are perfectly good bases for the same vector space V, right? That means that I should be able to write any state as a linear combination of either basis vectors. So for example, I can always find some numbers that do this, I runs from 0 to 1. At the same time, if I choose to express it in the y basis, I should be able to also write it in terms of some coefficients vi, where this is, well, this is b, let's say sigma, and this is y sigma, and sigma is equals to plus or minus. Okay, so sigma just is a label. It tells me do I treat it as a plus or do I treat it as a minus. So this just means b plus is just a number. I'm just giving it a name. Okay, so there's nothing deep about it. It's just a b plus b minus thing. It's not an operation. Okay. So my question is, since this same vector has two different expansions, let's convert them. I'm sure you've done this in the past. So let's suppose that psi equals to, well, let's do a simpler one, 2, 0, plus 1 plus I, 1. Okay, so I've given you this vector, written it this way. The question is, what is it in terms of the plus and the minus? So I'm asking you to calculate this guy and this guy. What are the coefficients in front of the plus or minus states, if I write it in that basis? Anyone? All of you took linear algebra. Some of you have A's in it, so this should not be a hard question. Any suggestions on how to proceed? Anyone? Suggestions? How to proceed? Otherwise, we just sit here. Good. Then we can redo a semester's worth of linear algebra, shall we? You learn more from the campus, right? Just learn linear algebra. Any suggestions on how to proceed? Okay, maybe not the answer, but just what's your thought process? How would you use that? I'm sorry?
Matrix multiplication.
Of what? Which matrix?
Of the coefficients of the plus and minus vectors.
The y plus and minus vector. So sorry, I meant to say y plus here. Y plus here. Matrix multiplication of what, sorry?
The coefficients of the plus and minus vectors. And multiplied by the coefficients of the 0 and 1.
So you mean take the coefficients here, 1 square root 2 I square root 2, multiply that by this guy.
Yeah.
But how do I get the correct answer? Like, how do I know? Okay, here's the here's one way of doing it. There are many ways of doing it, but here's a simple observation. So we're trying to ask, we know for a fact, right, that this can be written as something plus something minus. And let's put the unknown coefficients as b plus and b minus, as the notation suggests, or how I use notation. And my job is to figure out the b plus and b minus, right? But I want to isolate the b plus. How do I do that? Well, notice that if you take the entire expression, and if you hit it with the y plus here, so on the left hand side, we get this y plus psi. On the right hand side, we get b plus, y plus, y plus, plus b minus, y plus, y minus. But we just did a calculation where y plus and y minus were shown to be orthogonal, in fact orthonormal, right? So that right hand side simplifies so nicely. This goes to 0. That's by our calculation. This goes to 1. And so we immediately have on the right hand side just b plus. So what does it mean? It means that I can calculate this coefficient b plus simply by taking the overlap of the basis vector y plus with the steep thicket side. Okay? And this should not be unfamiliar because what this is saying, what this left hand side is saying is that if you have a vector, you're just finding the component along this direction. That's literally what the b plus means, right? How much weight is there along that direction? Okay, let's do a calculation then. Okay, so y plus, you have to form again, you have to form the graph, so that's 1 over square root 2, 0 minus I. Everyone following that? So that's the graph. And the cat, what's this guy? That's what's given to you. So twice of 0 plus 1i, 1 plus I of 1. Okay, good. Everyone okay? Following? I've just plugged in whatever was given to me. Now I'm just going to expand everything, but once again, noticing that 0 and the 1 state are orthogonal, then I just have to match up these guys and these guys. Sorry, this should be a 1. This should be a I. Okay. Right? We just have to match up those guys. And that's equal to 2 over square root 2 times 0, 0 minus plus minus I over square root 2 times 1 plus I. And this is 1, 1. Okay? Everyone agree? And next, I expand it, so that's equals to 2 over square, so that's equals to square root 2 plus minus I over square root 2, 1 plus I. And, okay, from there you do a bit of simplification. You know, if you really want me to do it, let me do it. Square root 2, and then that's equals to plus 1 over square root 2 minus I over square root 2. Okay, so that's the weight along the direction of y plus. I hope you notice a few things. The coefficient is complex, as it should be, right? In general, it will be complex. For example, if you work in a real vector space like position, then yes, obviously the position vector is comprised of 3 real numbers, x, y, and z, and they are real. So you ask how much weight is there along x, it must be a real number. But because we're working in the complex space, so yeah, the coefficient is complex, nothing wrong with that. Great. Okay, then we can repeat the same for y minus. Alright? So what do we do for y minus? Well, obviously, we sandwich it with y minus on this side. becomes 0, and that becomes 1, and that becomes minus. And so that allows us to extract the weight along that direction. And if you want to repeat the same count, so this is b plus. And so a b minus would be this. 1 over square root 2, 0 plus I 1. So again, where is that coming from? That's coming from the bra of this guy times the statement set. And okay, let's just do it. Square root 2, and then we get plus I over square root 2 times 1 plus I. And therefore we get square root 2 minus 1 over square root 2 plus I over square root 2. Okay. So yeah, that's b plus and b minus. If you encounter such things, you can do a consistency check, right? So so the reason why I'm going through this with you like very meticulously is because you can formulate these questions by yourself. You don't need me to formulate these ones. But I'm just giving to you so that you can see for the first time what's happening. So what's a great consistency check next that you can ask yourself? You don't have to wait for a professor to tell you to do this. You can say, if I want to check that my calculation is correct, then maybe I can do a calculation where I compute the norm of this guy, and the norm of that guy should be independent of how I express it. I should get the same answer, right? It's the same length. Like, who cares how I describe the state? It should be the same length. Okay, so let's quickly do it, right? So in this representation, let's ask what the overlap of psi and psi is. And instead of painstakingly writing it out in full, but by the way, if you're not comfortable with this, you need to practice this. Inevitably, there will be people who will not practice this and then lose a lot of marks during the test. So practice this, please. But for me, it's like this. I see 2 and 1 plus I. I can skip a lot of steps already. I'm not suggesting you do it, but you need to train yourself to do it. Okay, the overlap is you need to take the bra and cat of this guy. But I notice again that I only need to consider the diagonal pieces. So that is 2 times 2 plus 1 minus I times 1 plus I. I've skipped everything in my head, right? But you can follow what's going on, right? This 2 comes from the bra, and this 2 comes from the cat. This 1 minus I comes from the bra, this 1 plus I comes from the cat. And there are only 2 terms because the 0 and 1 states are orthogonal. And so that's equals to 4 plus, and that's equals to what? 1 plus 2, that's 2, right? And this is 6. Right? So the overlap in the state is 6. Now let's do it here as well. So we just calculated that b plus is square root 2 plus 1 over square root 2 minus I over square root 2, and b minus is equals to square root 2 minus 1 over square root 2 plus I over square root 2. So what's the norm of the state in this representation? Well, the norm of that state is just so the norm of this state, in this representation is just b plus plus b minus minus. All agree? Okay, so let's just expand it. So this equals to square root 2 plus 1 over square root 2 square plus, and then I need to take the square root of that. So it's 1 over square root 2 square. So that's on the first term. Second term is this. And next term is this. And anyone wants to just expand it, you should get the result. Okay, from here it's just an exercise, you get 6. Okay, and everyone okay with how I just simply wrote down the overlap in this basis was E plus absolute value square. Okay, not sure, then we need to go and read the notes. Good, that's a recap, okay? And this encapsulates what you learned probably as what is a change of basis. Right? You at some point you may have written down this matrix which is a change of basis, and then there was some confusion as to what to put on the rows and columns and all that crap. What's confusion is because you memorize stuff, but here you follow the logic. Logic is very simple. You have a state that is written as a linear combination of basis vectors. And if you want to extract the component along one of the directions, it's very simple. Just apply the bra onto it that extracts the component. That's the whole point of the bra. The bra will extract the component along that direction. Okay, and that leads me to my next operator, my next topic, which is now moving back to operators. Okay, so we were talking about linear operators, or operations, or maps. So we learned one of them, which was the bra. This is recap. We learned what the bra was. So a bra, as the name suggests, always wants to eat some cat. So a bra wants to munch on a cat to form a number. Okay, so that's the purpose of a bra. This is a map. It's linear. Okay. But now let's talk about something also quite simple. Let's have a vector space, V. And point in it, of course, the vectors, alpha cats. And let's have an operation where I send every vector back to itself. So it does this. It maps and comes back to itself. You take a different vector, beta, you map, and you come back to itself. Okay, fine. Let's give it a name. Let's give it the identity operator name. As the name suggests, the whole point of the identity is to do nothing. It's to send a vector back to itself. So the identity is such that if you apply it to a vector alpha, for any alpha, it comes back to itself. Example, and I'm sure you guys know this. Again, position vectors. Let's do, say, Rx, Ry, Rz. Then what's the identity operator on this vector? Of course, it's 1, 1, 1, 0, 0, 0, 0, 0, 0. Acting as Rx, Ry, Rz. That's back to itself. Right? The matrix is an identity matrix, but I want to be more abstract and say, let's not think about matrices. I mean, it's okay to think about matrices, but it's an operator, right? The operator is abstract operator that lives there. Okay, good. Next question. Let's suppose that V, this space, has an orthonormal basis I, which runs from 0 to d minus 1. So it's a d-dimensional space. There are d different elements in it. Okay. Good. Alright. So what do I want to do next? I I want to say, so if this is an orthogonal basis, that means that any vector alpha can always be written as some linear combination AIs of the basis vectors R. Everyone okay with that? It's a basis, right? Now my question is, what is AI? I don't mean it in a philosophical sense. I mean, how do you compute AI? I'm sorry? Exactly. You take the overlap. Okay, so to extract AI, as I've taught you the last 10 minutes, take the overlap with the ith state. Okay, but let's be careful here. This sum runs over this index I. So I should not put overlap with state I here because that's using the same notation. Okay? So if I want to be safe, let me relabel it to be J, which I can always do. Like that's just a change of what I mean by the counter. And let's take the overlap with state I. So from this defining equation, you get this. AJ, IJ. Okay, how does it help us? But we realize that it's orthogonal. So this guy is delta IJ. And again, what's the meaning of delta IJ? It's 0 everywhere, except when the jth term is equals to I. So in this sum, everything is killed, everything goes to 0, except one term, the AI term, is AI. So bam, we get this. I overlap with alpha is equal to AI. Again, nothing too shocking is what I told you before. The component, the coefficient in the ith direction, just amounts to taking the overlap of I state with alpha. But then, let's use this back into this definition of the state. Okay, so let me erase this calculation. So the 8th, jth coefficient is nothing more than that, right? So I can rewrite it as this. J alpha J. Okay? Okay. Now a few things. I'm going to move this number over here. And that's fine, because that's just a number. In general, you should not do this because matrices may not commute. You know, you apply matrix A first and B. That's not the same as applying B first and A. But in this case, because it's just a number, I can do it. And let me do it. So that's equals to J equals to 0, V minus 1, J alpha. Okay, this equation seems a bit circular. It's like alphas on both sides, but there's nothing wrong with it. So what it is saying is that for any alpha, it can be re-expressed that way. On the right hand side, this complicated mess. This means that if we now treat this object, if we decide to break up this bracket as the overlap of a bra and a cat, then I can treat this as one object. And what is this object's action? It's saying that it hits, let's call this operator T, T acts on alpha to give me back alpha. And that's true for any alpha. So bam, T is the identity. So what we have learned is that this is the dyadic representation of the identity, which is, okay, so a dyad is this, so this is a dyad. A dyad is just two elements. So here, this is what is known as an outer product, as opposed to an inner product. Outer product, because the arrows are pointing the other way, so it points out outer as opposed to inner product. And so we have this identity. The identity operator can be written as j equals to 0 to d minus 1 of jj. And this would be exceptionally useful. So everything that we will encounter. So let's give a bit of physical interpretation to what this object is. Alright? And because I also want you to be able to look at an equation and get a picture out of it. It's not just for memorizing it, it's for telling a story about it. So on the left hand side, this big I is the identity, is a do nothing operation. Its instructions are do nothing to the vector. The right hand side has a meaning. It's saying that, now if you ignore the sum first, let's just look at the first term here. It's saying this. It wants to eat a vector alpha, and in doing so, it will extract the component along the j direction. And then when you multiply that component with the vector j, it's saying reconstruct it in the j direction with the length. And then the sum just says do it for everything, do it for all directions. And because this is the basis, then it must reconstruct the entire vector itself. So this object on the right is saying project the state alpha onto the direction j, then reinitialize it in j with the appropriate length, and then sum over all possible projections. And that's it. That's what identity is, literally, right? Decomposing it and reconstructing it. It's like destroying it. It's like moving all the small parts and then reassembling it, like Lego pieces, right? Okay. Good. Examples. Example. So let's look at the space of position vectors in R3. Let's say R3 is. So you're used to saying that the position vector be Rx, Ry, Rz. That's totally fine. But what's the basis for this space? Well, the basis is this: Ex, Ey, and Ez. And we knew beforehand, like from your previous studies, that the identity should be 1, 1, 1, and 0 elements. So whenever I don't fill out the entries, I mean 0. Okay, so according to that rule, it's saying that if I take the outer product of Ex plus Ey plus Ez. Let's do it. So in matrix representation, this is column vector 1, 0, 0. That is 1, 0, 0 plus 1, 0, 1, 0, 0, 1, 0 plus 0, 0, 1 plus 0, 0, 1. And yes, if you multiply everything out, you get 1, 0, 0, 0, 0, 0, 0, 0, 0 plus everything 0 except 1 here plus everything 0 except the 1 here and therefore you get 1, 1, 1. Okay, kind of a trivial example. But you know, you don't have to describe position vectors using ex, ey, ez as this basis vectors. Let me do a change of rotation which you may have encountered. Let's do this. 1 over square root 2, 1 over square root 2, and 1 over square root 2 minus 1 over square root 2. Sorry if you can't see it. But basically I just changed what I meant by ex and ey to be 1 over square root 2, 1 over square root 2. Okay, then according to that representation, that should still be identical. But now what's changed here? I get 1 over square root 2, 1 over square root 2, 1 over square root 2, 1 over square root 2. This should be 1 over square root 2 minus 1 over square root 2, 1 over square root 2 minus 1 over square root 2. And so if I multiply everything out, I should get 1 half, 1 half, 1 half, 1 half, 0, 0, 0, 0, 0. 1 half, 1 half, minus 1 half, minus 1 half, 0, 0, 0, 0, 0. And this should still be the same because I didn't change it. And indeed, it is still 1, 0, 0, 0, 0, 0. Yes? Okay, so the identity is many forms, right? Give me any basis, orthonormal basis, and the identity can be expressed there. Okay. So we could come back to the first example I gave during class, where I said that this was an orthonormal basis for the two-dimensional vector space. So which means that the identity can be written as 0, 0 plus 1, 1. And that kind of makes sense to say that, you know, again, there's some component along 0 and there's some component along 1. So every time you want to eat something, suppose it eats an alpha, it just spits out a component along 0, spits out a component along 1, and then reconstructs it. But we also showed that the basis y plus and y minus was also orthonormal. So that should also be valid. We can also use that as in the resolution of the identity. And let's show that then. So recall that y plus, for the example, I gave only one. The example is this. Y plus is this, y plus minus is this, 1 over square root 2, 0, plus minus I 1. Okay, so we need to form y plus, and y minus, y minus. Let's do the first guy. That is 1 over square root 2, 0 plus I 1. Outer product, the graph, which is 1 over square root 2, 0 minus I 1. Here, please do not rush. I said that there was a trick for the inner product where you can just look at the diagonals, right? But here we're not doing the inner product, we're doing the outer product. So just keep everything. Just don't rush, just think about it. Just do, so if you expand it out, you get 1 half times 0, 0 plus I minus I of 0, 1 plus I of 1, 0 plus 1, 1. And the next term, this guy here, is pretty much the same. So you get 1 over square root 2, 0 minus I 1 times the bra, which is 1 over square root 2, 0 plus I 1. Do you agree? So we add minus 1, 0 plus y1. And then we notice many cancellations. Cancel, 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 cancel. Then we get 0, 0 plus 1, 1. Which I said was the identity. Okay, good. And so again, we see that the identity can be expressed as outer products of on orthonormal basis. I cannot help but throw you another nugget of interesting information. Maybe this will hopefully pique the curiosity of some of you. Sorry, was that too quick here? Yeah? Everything okay? Okay. So here's a purely more mathematical example, but I think it's also quite interesting. Okay, so let's consider this space, right? Let's say that we have an interval from 0 to 2 pi. I'm just considering a small interval. Let's say that x lives in 0 to 2 pi. And then I'm going to draw some function on it. It could be a complex function, so some function. And let's say it repeats. Okay. And let's say that the function is such that if I integrate from 1 to 2 pi, from 0 to 2 pi, of f of x, and I think the mod square of that is less than infinity. So it's normal, it's square normalizable. The reason for this is because I don't want functions that do this. That blow up, go crazy. I want something nice, like some bounded function, an example of that would be a sine function, cosine, all those are nice functions. So this space of f of x satisfying this is called the L squared normalizable space. Never mind what the notation is, but the idea is that, hey, you have a bunch of functions that's living on this 0 to 2 pi, and we don't have functions which just explode, so they're nicely behaved. Good. I claim to you that this space is a vector space. So again, what does being a vector space mean? It means that if I take two functions that obey this, if I take a times of f1 of x plus b times of f2 of x, and I call it g of x, for a and b some complex numbers, then again you'll find that g of x squared is less than infinity from 0 to 2. So the space is very nice. You can add two such functions up. You'll again get something which is square normalizable. Now here's a fact that you may have encountered before. Since this is a vector space, we should be able to talk about basis. We should be able to talk about dimensionality of the space. So what's a nice basis set for this space? Anyone? Anyone? So the question is, what's the basis? Let me remind you that There's not a unique answer, of course, infinitely many bases, but what's a nice, convenient basis that you have probably heard of before? Hopefully you've heard before, hopefully in mathematics. Does it ring a bell? Yes? No? Great, thank you. Sines and cosines. Okay? So if you look at this function 1 on that interval, and you look at sine of nx, and you look at cosine of nx, and n is some integer. So in this case, I think should it be natural numbers? So this big N just means N just runs from 1, 2, 3, 4, 5. Then this is a basis, and this you have heard often called as a Fourier series, right? Any function on this interval can be written as some constant plus some an sine of nx, sum of that, plus some bn cosine of nx. By the way, again, if you want to extract the coefficient of an and bn's, how do you do it? Take a draw, apply it there, right? You do whatever I taught you in the past 10 minutes, right? Past half an hour. Take a draw, and you can extract the an's and bn's. And here's another example of a basis set, which is, I prefer this, but it's not necessary. It's just complex explanations. So n goes from n to the integer set. So that means that I can also express f of x as some linear combination of e to the power of I and x. Sorry, this is minus. Okay, good. Okay, so now we have a basis for this space, and we know that functions of that form can be written as in terms of these complex exponentials. Let me ask you the question. What is the identity operator in this space? So I want an operator where I take identity, I multiply it by f of x, I get f of x. So you might say, clearly that's 1. And that's not the correct answer, okay? Because 1 is a function in that space, and we have no notion of multiplying 2 vectors, except the inner product, but this is not. So we want a linear operator that acts on a polynomial that spits out a polynomial. So we actually want this. We want, in this language, what this means is that we want some linear operator that takes in x prime and spits out x. And when we integrate over dx prime, that should give me x, f of x. This is what the identity operator is. Very good. And what was this operator? So you may have learned it in electrodynamics. If you plug in the delta function here, so here this is the direct delta function, not the connected delta, but basically it's, you learn this as something that is infinitely spiked at x minus x prime, and 0 otherwise. Then it returns the value of the function at x. So that's your direct delta function. Now it seems like a very mysterious object, right? It's like, okay, I can memorize rules and all of that. representation. If it is true that the identity can be written as an outer product of orthonormal basis values, which by the way, this is orthonormal. Which you can check, so like literally you can check. So under the inner product, which is, G star of x, f of x, from 0 to pi. So that's what it means to do. Okay, so this is the orthonormal basis. If you treat that seriously, that is saying that the direct delta function should be writable as the sum, according to that, over those basis elements. And these basis elements run from n and m. Oh, sorry, n open, sorry. Going from minus infinity to infinity of e to the power of I nx times e to the power minus I n x prime, which by the way is x minus x. So that's the direct delta function. And let's have a bit of visualization. So this sum runs from minus infinity to infinity. That's a bit hard to visualize. Well, let's just use human intuition and just say, let's let the sum only run from over one term only. Okay. So n equals to 0. If I ignore everything else. So if I only keep n equals to 0, I'll get this function. One function, right? But if I take n equals to 1, if I include minus 1, 0, and 1 in the sum, and I ignore everything else, then I get this 1 plus e to the power of I and x minus x prime, 1 plus e to the power of minus I x minus x prime, and that is 1 plus 2 cosine x minus x prime. Okay, well, we know how to draw this. So this function looks more and more like this. Looks more like this. How does it go? So this axis is x minus x. So if I keep n equals to minus 2, minus 1, 0, mark 1, and 2, then you can repeat the same exercise. You get 1 plus 2 cosine x minus x prime plus 2 cosine 2x minus x prime. And then what you'll see is that this will start looking like this. And if you keep going, you keep doing this. As n increases, as the number of terms you keep, number of terms count. And in the limit, when it's infinite, then you get this. Precisely what you want. This is called the Dirichlet kernel. Okay, this was just fun. Okay, good. Okay, so don't worry about this, but if that piques your interest as to where the delta function comes from and what Fourier analysis is really just resolving the space of L-squared functions into a basis set and then applying known results from vector spaces there, so on and so forth. Now I ask my TA to come and set up the flashes the questions on the screen. Feel free to go to the toilet for a few minutes, come back. If you want to leave, up to you. Feel free to dismiss yourself at 11:40, 11:45, whenever you want to go. Okay, but this session is really for us to interact. Okay, and ask questions. Okay, Richard, please.
What time did you? Hey, you get it, right? I was like, I wanna see. But then, private, I didn't want to take speaking companies. But then instead, I wanna do like for real, speak for real. Then I reach home and talk about it. Then I woke up at I think like 11 plus. Then I watch my lecture, and do some work, and I look at something, not what I think 4 o'clock already.
Okay, so the if I'm not wrong, the same questions are on Canvas, right? You uploaded them?
Yes.
Okay, so they're already on Canvas. If you can't see them, just try them. First few questions are more about classical mechanics, just to do some recap. But I think what would be most helpful is if you guys can try exercises 4 and 5, for example. 4 and 5 would be much more helpful for, more directed for this class, in the sense of like, it will help you in achieving facility and doing calculations. Okay. But I think we can just flesh out all the questions. Can you see? Yeah, I think that's fine. Okay, I hope everyone's eyesight is good. And not graded, so just do whatever you want and try it out, because I found that in the past when people try it out on the spot and they realize that they have misconceptions, then they get asked it right now. we discuss, discussions are totally inquiry. You will learn best and talk to your friends. Yeah. Get to know your TAs as well.
So I just
Yes, correct.
yeah, you got yellow. Yeah. Yeah, no, okay, now it makes sense. Like, does that still computers?
During MM1, did they teach this stuff like they racially?
What?
During MM1, did they cover this stuff?
Not all, but like the most part, yeah.
For the most part. Okay. Is it like a lot of the part is like cover after because I only went came the first half.
After you came. Maybe after you left.
Oh.
Yeah.
process was here we derived that the identity is decomposable.
You doing something one? Oh, I doing 4 and 5.
Oh, I mean, it's the question.
If you don't 4 the whole thing. That part.
Wait, I'm the time that's question 4, sorry.
Oh. What year? Like that. What's it?
A is C1, A1 C0.
Ah, yeah.
Yeah.
I mean, you can straight away see it.
What is this? What year at this? Isn't this proportional to? Huh? Yeah? Huh?
If you sit back and say
I mean, because whether it's like basis vector just means it's normalized vector. I think I get what he's trying to say. Like the proportionality just means that the scaling factor is
Oh, okay. I get. Because
what is it? It's just supposed to zero.
This is a condition for normalized
Don't worry.
Why did you write? Why did you write it?
Oh, I'm asking you to scale it back.
Yeah.
I'm asking you to multiply that by the total number. So that is also what's in bracket.
Oh,
So the only difference
it's just
direction.
yeah.
I only told you that it must be somewhere along that direction. And now I want you to fix the vector by fixing the vector.
Okay. Yeah.
You could have just said that the upload y is equal to k times blah 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 5k.
Yeah, I know. I'm just wondering.
Interesting.
Yeah, it's in like
Which part?
I get it, but I want to know why.
Or maybe some deeper reason.
Yeah. Because usually you be like, this is the vector, your vector v. Then find the probability of x on you put proportional like it's like really the by right correct. It's like that time we learned eigen value. It's like there is no like one correct one because it can be scaled up and down. Because you can always pull out a common factor. Same thing Yeah. Like, oh damn.
You see that
I have to go for auditions. Pretty long day, bro. Hey, you know yesterday, wow, I was trying so hard not to laugh at this guy. No, the guy is terrible. Like, if you come to audition, you don't feel at ease and you can feel
You're auditioning,
yeah, I'm judging you. Yeah.
You actually judge people as well.
when is that how you judge me?
We had one solution. I actually couldn't hold it in. I ran out of life. I went there. No, wow, it's terrible. I was like, couldn't even look at him. I had to stand at the table. Say, don't laugh, don't laugh, please don't laugh. The moment you use it for guitar, he can listen. The wrong person was like doing some letter. It's supposed to look cool, you know, like all the guitars and just started hitting it. Yeah. Yeah, of course, last year you wanted to join. Amazing.
You think after French fry, French fry?
Gymnastics.
Are these is the solutions or these uploaded link?
Oh yeah. You can just ask us out. You can just ask us out loud. It's fine. You got any particular question?
Yeah, let's see question. Just now they say do question 4 and 5.
4 and 5?
Okay, let's see question 5.
Oh, okay. Yes. Question 5. Have you given some thought? Have you finished the proofs? Exercise 2 and 3. Have you already finished the proofs for exercise 2 and 3?
Oh, 2 and 3 not yet.
Not yet.
So I should do those first.
No, those are. Okay, so exercise 4 you have done, as I can see. Yeah, those are more application wise, and exercise 5, 2 and 3 are more the fundamental theorem, like a proving type. I would suggest that you go through. Yes, I would suggest that you go through 2 and 3 first before you attempt 5. But then, basically, it can be a homework, like refreshing up your linear algebra, like what type of spaces qualify as a linear space.
Properties, question 2, using properties 1 to 8.
Yes, there are 8 properties that defines a vector
it's not
space.
here.
Oh, properties? No, those are on the lecture notes. Yes. Have you seen the lecture notes, or has Prof. covered it? Yes, these are the properties. Yeah. Yes. You have vectors. You have its complex numbers as the field, like coefficients. Like you have scalar, multiplication, vector, inner product, and stuff. Yes. But then, just a hint to exercise 5, you need to make use of the linear independence between the set of bases. So you can try to come up with a counter argument, like suppose. Okay, so the question is to show that every V permits a unique decomposition. Then what you do is that suppose that this V has two distinct ways of decomposition. Can you find a contradiction? Yes. That's how we go about proving such a statement.
Will they test this in exam?
Oh no, this will not typically be in the exam. These will not be in the exams.
No, I'm trying to find. Huh? You mean exercise 5? Yeah, exercise 5.
Then that's for this mod is like PDE's tester.
PDE? Okay, PDE?
Like
Partial differential equation.
Is it part of this?
PDE is no. They will not be the focus of the exams, if you will.
ODEs have ODE.
ODE stands for ordinary. Yes. So basically, like you have ordinary derivatives and you have partial derivatives. Like ordinary derivatives are d by dx, d by dt. And then partial derivatives are partial by partial. Those are multivariate calculus. Yes, but then I would say not to worry that much because this course is not exactly dealing with PDEs all the time. Later on, you will.
For me, I took the math modes, like the multivariable calculus and
Oh, you read it? Yeah, that's great.
I didn't take math methods.
You didn't take math methods.
So like a lot of stuff I haven't heard before. Dirac delta function.
Oh, yeah.
Or the Fourier. Just now you mentioned Fourier series also.
Yes, it'll be nice to know a bit about Fourier as you go along. Yes.
So all this is when you mention, it's not just like good to know, but like I actually have to know for this. It's not just like bonus knowledge, but I have to know like Fourier series, Dirac delta function.
Yes and no. Like you don't have to know it as an expert. Yes, knowing a bit will be helpful. Like because essentially where you're going to use Fourier the most is when you need to do change of basis in an actual problem. But then knowing a bit would be helpful. But then yes, I'm sure you pick them up as the course goes along, because when we will give I suppose we'll give more materials when it comes to it.
I need help to learn this in AI. Like, are you available?
Yeah, of course. Shoot us a message all the time. We're here to help. Yeah.
Is it through email?
Emails like okay. So like if you go to the Canvas, I'm not sure how Canvas works, but then yes, in the course notices, in the course notifications, there should have been a page where we have posted our emails.
Oh, this is from 1 to 7 to judge people.
To join the
50,000. You know, yesterday I was trying very hard not to laugh at this guy. Yeah, I had to stare at the table.
The coefficients are numbers.
It was damn fun.
The vectors are
You know when like you're like this, but then you try a bit too hard, then it just ends up as a disaster.
you try hard at playing or
No, he's playing. He try a bit too hard. Yeah, try to do all the small flashy things, yet end up with disasters. Yeah, it's hilarious. No, I have introduced until 7.
Yeah, this is actually
1:30
It is not yet orthonormal. It's just the basis. And on this mathematical formula, this vector space does not have to have an inner product to start with.